Hi everyone. The subject of my talk today is B-coloring of regular graphs. Let's start with the definition of proper coloring. By a proper coloring, we understand an assignment, colors, numbers to each vertex in such a way that any two adjacent vertices are assigned different colors. So we avoid monochromatic edges. And usually in many problems connected with coloring of graphs, we are interested in the smallest number of colors, admitting the desirable coloring, type of coloring. And in the classical model, the smallest number admitting proper coloring is named chromatic number. This time, we are interested in the largest number of colors. Of course, what is the type of coloring? We are interested in such a assignment colors to vertices in such a way that every color class, we mean the subset of vertices that are assigned the same color, each color class need to contain one vertex, at least one vertex, that has a neighbor in each other color classes. We name such a vertex as B vertex, and here we've got an example. We have a Peterson graph. We have three colors here, red, blue, and green, and we can observe that each of these color classes contains at least one vertex that is assigned to any other color class. For example, here we've got B vertex for blue classes. This vertex is colored also with red vertex as well with green vertex. For red color class, we have B vertex, for example, here. This vertex is also adjacent to any other color class. And for green class, let's say we can take, for example, this vertex is B vertex in a green color class. So each color class contains at least one vertex with such a property that the vertex is adjacent to other color classes, each other of our color classes. And we can observe easily that the bichromatic number, so the largest number of colors, is not less than classical chromatic number in a when we color graph in a proper way. So when we are interested in the largest number of colors, so this number cannot be less than the smallest one. And from the other side, we have an upper bound given by maximal degree of a graph plus 1. This is connected with the observation that if we have, maybe here, if we have K coloring, and we have K color classes, let's say V1, V2, up to Vk, and we need to have, it must be a B coloring. Each color set must contain a vertex, B vertex, that is adjacent to any other color class. For example, here also we need a vertex that is adjacent to any other color class, and so on and so on. We see that these B vertices must be of big enough degree. So if we want to achieve B coloring with K colors, we need at least K vertices of the degree K minus 1. So it's rather natural to count how many vertices can play a role of being candidate for B vertices, and we count the degree of each vertex in a graph G, and we order these numbers in non-increasing way, and by a M of G, we denote the maximum index, the largest index of vertices, such that the degree of vertex Vi is at least equal to I minus 1. So here is the bound. Here we've got candidates for B vertices. The rest vertices have their degree is too small. So we also estimate bichromatic number in the language of M degree, and it was proved that bichromatic number is not greater than the M degree of the graph. And there are a lot of papers according bicoloring, maybe not a lot of, but certainly some. And part of them concern the subject of bicoloring for regular graphs. These quite interesting graph classes from the point of view of bicoloring, because we know exactly what is the value of M degree of every D regular graph. Each vertex has degree D, each vertex. So we have D plus 1 vertices of degree at most D. And it turns out that for regular graphs, first, it's clear that the bichromatic number cannot be greater than M degree, so we have this bound, but it turns out that in many cases, this observation, conjecture, that for regular graphs, we need exactly this number of colors for the optimal bicoloring. Optimal means, in this case, with the largest number of colors. And there were some investigations in accordance to this conjecture, and finally it was posted independently by two teams of people, and they say that if only we have a deregular graph with graph at least 5, it means graph is the length on the smallest cycle in the graph. So we have cycles of length 5, 6, and so on. We don't have cycles of smaller size here. And if we consider deregular graphs with graph at least 5, different from the Petersen graph, this one exception, then such a graph has a bicoloring with exactly D plus 1 color, so the upper bound is achieved. And we knew something about this conjecture. There was some investigation in this direction, and we, for example, know that if only we have deregular graphs with this number of vertices, so the order of the graph is big enough, then independently on the graph of the graph G, we have B chromatic number equal to D plus 1. Some years later, this bound was improved to this amount, to this number. If we have a graph with at least such a number of vertices and graph is irregular and d is not less than 7, then also we know that the conjecture is true. Let's observe that on the basis of these two theorems, we can conclude that if we have given number d, if it is fixed, there are only finite number of connected d-regular graphs where we don't know the exact value of bichromatic number. And because there are graphs with order smaller than 2d to the power of 3, or here this amount of vertices. So it seems that the situation is quite good, but finite means here not small. We have still a lot of cases of graphs that the value of bichromatic number is unknown. And we have some other results according to the conjecture. For example, if we consider graph with no 4 cycle, 6 cycle, then we know the value of bichromatic number. We know that if the GERF, so the smallest cycle in the graph, is at least 6, we are also done with the conjecture. The conjecture is true. And so on and so on. We have some nice results according to the conjecture. And if we summarize all these results, we can conclude that we are left with only some d-regular graphs, and the number is finite for each d. We are left with d-regular graphs of degree at least 7. We know that our d-regular graph contains at least one C6. And we know that the order of the graph is less than this number. In other cases, we know that the conjecture is true. So we are only left with such d-regular graphs. So we started to do something to decrease the number of unknown cases. And it's rather natural that we consider the smallest 7 regular graph with GERF exactly 5, with cycle C6, and with the smallest number of vertices. And we found such a graph. It's very known, well-known example of a graph. It's a Hoffman-Singleton graph on 50 vertices. It has a lot of nice properties, and we know that we are able to color this graph in B manner. Yes, that's in such a way that each color class contains a vertex, at least one vertex, being adjacent to any other color class. And we with D plus 1 means 7 plus 1, 8 colors. So this is the smallest example of the cases that we are left with them, but we already know that also for this case the conjecture is true. Okay, what's more, what we are able to do more? We tried to focus on d-regular graphs that we are they contain at least one cycle C6, because if a graph doesn't contain, we are done. We know that the conjecture is true. So certainly we need to consider the regular graph with at least one cycle C6. But if we are able to find at least one vertex in the whole graph, the vertex X, that is not contained in cycle C6, then we are also able to prove that such a graph can be admits B-coloring with exactly D+1 colors. And let's start from some observation, and then we pass to the proof of the theorem. First, if we take vertex X, there is no contained in cycle C6. We know this is the regular graph. We know that there is the regular graph. So we know that this vertex has the neighbors. We have x1, x2, x3, xd. And of course, there is no edge between these vertices, because we know that this graph is irregular with GERF exactly 5, even exactly 5. So the smallest cycle has length exactly 5. So we know there is no edge here, because if it was, we could have then cycle C3. So we know that there is no edges between neighbors of X. And next, we know that each vertex, of course, is adjacent to D-1 vertices, because the degree is also D. So we have x11, x12, x1, D-1, and so on and so on. Here we've got the same, we say, bunches. And it's easy to observe that the bunches, the neighbors of vertices of type xi, are disjoint. Because if there was a vertex that is common neighbor of of these two vertices, for example x2 and x3, here we could have C4. And we know that the smallest cycle has length exactly 5. So C4 is not present in this graph. So we know, and this is the observation, that the neighborhood of each xi has only one common vertex. It's a vertex X. And here we've got in each case, in the case of each vertex, D-1 disjoint vertices. Yeah, so we know that here is not possible to have common one neighbor. And next observation is that the graph induced by neighborhood of two vertices xi and xj is emerging. The graph induced by this, maybe we can draw something. We can draw. We have vertex x. Here you've got xi, xj. Here we've got is D-1 neighbors. There are also D-1 neighbors. And we know that between two bunches, we have only matching, and the graph induced consists of isolated vertices and some matchings, because if it was such a situation that one vertex has one neighbor in the next bunch and the other, so here what we have? We have 1, 2, 3, 1, 2, here. Here's C4. It's forbidden. So certainly each vertex has at most one neighbor in the next bunch, in any of other bunches. So between two bunches, we have independent edges, and maybe some vertices are isolated if we consider the graph induced by this bunch of vertices and this bunch of vertices. Yeah? The next observation says that each neighbor of, we say already that we have each neighbor of each such vertex is a neighbor of at most one neighbor of others, because it's also not possible if we have, let's say, I and X, A, and it's not possible that the vertex has one neighbor in one bunch and the second neighbor in other bunch. If it was such a situation, then let's remember that here we've got vertex X. If it was such a situation, we could have what we could have. Let's consider this vertex, this vertex, this vertex. Here we've got the neighbor, here we've got the neighbor, and together with vertex X, we could have C6. Of course, it's allowable in the whole graph, but let's remind that we assume that vertex X is not contained in cycle C6. So such situation is also forbidden. And what we have here, on the base of this free observation, we are able to prove our theorem that if only the vertex X is not contained in cycle C6, then the conjecture is also true. I will omit the rest of the proof. I think the main idea is the most important. And we can ask, okay, what is the number of cycles that each vertex is contained in? And we still are able to prove that the conjecture is true. And I put here the number 5, but it's only sample number. We are able to prove also for bigger numbers of cycles. Nevertheless, our aim is to put here the as big number as we are able to manage. And we assume that there is here this expression, the function of D, depending on D, the degree of the graph. And for us, it's still open problem. What we can put here, what is the biggest number? Of course, it should be here the biggest number of cycles that every vertex in the regular graph is contained in it, but our goal is not so big. We are interested in putting here expression that our method given in the previous proof and the proof of this theorem still works, and it's our open problem, and the goal for nearest future. And exactly here is our question, how big the band can be, that actually the conjecture posted by two teams of people is true. And is the good point to finish the talk. Thank you very much for your attention.